So one thing we are familiar with is that you've seen a lot of what do you call it, alternating current waveforms, right? AC quantities waveforms, and then one of the commonest one we've said so far is that the commercial one is this, which is the sine wave here, right? But then it is not always that you see it of this form, right? There are times that you see something like this. Okay, just to make things clear, the one that we are talking about right now is this red curve here, this, right? This is the one we are talking about now, this red one. So the commonest one is a sine wave, right? Which is this one we're speaking about here. But there are times that you don't have a sine wave, right? But then there's a way that we're able to represent a curve like this one right here, the one in this red here that I'm highlighting with the brown. There are times that you have a wave of this form, but then there is a way to represent this using sine waves, right? But the only difference is that you having different frequencies, but there will be multiples of the other, right? So let's see. What happens is that if you have what the whole harmonics is about is that if you're having a wave of this form, right, you can use other waveforms to describe it, but there will be other things added together, giving you that very same one. So an example is that if I have there's a wave, right, a square wave or something, right, which is written this way, right. So I'm going to use this example to explain how the whole thing is. So as I was saying, you have a complex waveform, right? And then one simple way to represent the whole thing is to use sine waves. There are ways of writing it to represent it. And when you do that, and then you have a different what do you call it? Different frequencies within the same sine wave. We call it a harmonic. So I'm just going to use this example. So let's see. So this is an example. This is actually the representation of a square wave, right? I'm just going to write this out. Okay, so we have sine 2 pi, and then what we've said so far is because we are actually representing the same wave, but then we are using different waves that are of multiple, what do you call it, the frequencies. We have a basic wave, it has a frequency, right? We'll call it fundamental, and then the other ones are just what's the name, having frequencies that are multiples of the one we call the fundamental. So I'm just going to write this out and then we'll look at it. So this is 6 pi ft. I'm just going to end here, but then I think it's actually a long something. But I'm just going to use this to illustrate what we are talking about here. Pi ft, and then we have this. So it goes on. So it's describing the sine wave, right? Square brackets. What we've been seeing so far is this. When we look at this, you can clearly see that. Okay, let's go one more time over this. We said if we have, let's say, a sinusoidal quantity, let's choose voltage, right? It could be written this form where we have some kind of like the peak value, and then we have the sine, right? And then we have angular frequency and something like this. We could be written as this Vm here, sine. This W will give us a 2 pi f, right? And then we have t, right? Okay, and we've seen all these clearly, right? Okay, so when we go over this, all that we've been saying about the harmonics is that it's basically composed of different wave functions in it, right? And because the wave itself is complex, and then we want to find a way to represent it, we use other waves to describe it. So in this case, we are just using sine waves to describe it, right? So this right here, this portion here is just on the outside of the whole thing equation, right? So mean that it's just a factor throughout, right? It has factored out, right? So then when we look through within this bracket here, these are the other things that we see. You get to see that we have this part here, we have a plus, and we have this part, and we have a plus, and we have this part too. The other thing, but we are just considering these three. So what we are seeing about harmonics is that we have a fundamental what's the name? A fundamental frequency within it. So let's see. Looking at this one, for instance, you see we have sine. There's nothing here, meaning that the frequency here, so the what's the name? The peak for this particular one here is 1 for this function inside, right? We've done some factorizations on the outside, but then we are just looking on the inside, assuming that there's no factorization factor, like there's nothing factored out, right? So we are just looking at that too, right? So meaning that the peak here for this particular one here is 1, right? And then here we have 2 pi ft. Looking at this, what's the name? The things that will go out are t and then pi, right? here too we can have pi and t out. We are not canceling now, we are just looking at something, and we have pi and t, right? So what you could look, the remaining that we see that here we have 2f, right? Here what do we have? We have what? So let's write them out. So here we have 2f, right? Here what do we have? We have 6f, right? This is basically kind of like the frequency. Here what do we have? We have 10f. So what that we're seeing is that we have just one. The original 10 is, then again, this example here is not for this wave. This is actually for a square wave, right? This is a square wave. This equation we've written here is for a square wave, right? Okay. And then we said that because the wave itself is complex, we are trying to find a way to break it down to other waveforms. And when you add these waveforms together, it gets the original bigger one, right? So yeah, that's what we are seeing so far. Okay. So now, here the frequency for this one here is 2f, here was 6f, here was 10f. So you can clearly see that any other 10 that comes after this one are just multiples of this very one here. That's what we mean by we say that when we say the frequencies of the other ones are just what do you call it? Integral multiples of one of them, right? So this is basically here what we call the fundamental waveform of the whole wave, right? It's having a frequency of 2f, right? This one here will be times 3 of this, 6f. This one here will be times 5 of this, giving us this, right? So this is the whole equation describing it. But then again, the basic thing doesn't change. It's just that it's made up a summation of different waveforms, putting them together give you the original one, which we call the harmonic or non-sinusoidal, right? Okay. So then again, still the same thing. For each and every one of them, we have the peak, we have the sine part, we have the, what do you call it? The angular frequency, we have the time, right? Which will break down and get this, right? Just the same thing. Okay. Now, so now that we have the understanding from the equation, we just look at the diagram and then we'll move on to something else. So let's see. All right. Let's. Okay. Okay. So now we have this, right? We are coming back to this. We've seen something from the equation, so we're just going to look at this one and make some sense out of it and then move on. All right. This one here is the time. This is whether what's it called, voltage or current, right? So what we are saying is that this right here is the original thing, right? This is the waveform, the original waveform, right? But then because it's difficult to represent or it's complex to represent, we break it down and get other waveforms, right? So when you look at these ones very well, we clearly see that we have a blue waveform there, a yellow waveform, we have a green waveform, right? What it says is that you have the fundamental waveform, which will be this, the green one here. So the green, I wish I could use different colors. So the green, so we have green, right? Which we call the fundamental waveform. And then we have the yellow. The yellow, let's see. So yellow. And then we have a blue, right? Blue. The differences are subtle, but we're just going to look at them. So this is the original waveform. The red one, as we talked about, the original waveform, right? And there's non-sinusoidal for harmonic. And then we've broken them down to get this green, blue, and yellow waveforms. When you put those together, it gives you back the the red waveform, which is the non-sinusoidal waveform. Okay. What this says is that, so we look at, let's see, for the original waveform, one cycle is about from here, right? This and then this, and it gets here. So from here to here is what we call one cycle, right? And then from here onwards, you see that when you go to the other side, it's like the other one has been reflected to the other side. So it's like the same thing, but then it has been rotated, right? So this one down, up, down, right? But this one is up, down, up. So it's the same thing, but rotated the other way. So now we've seen that one cycle for the original waveform. So when you look at this one cycle here, within one cycle, right, you're just trying to see why the frequencies are multiples of the other. So when you look within this one cycle of the red waveform, you see that. So let's write the names here. So we said the green is the fundamental, right? Fundamental. So if we are trying to represent the red waveform, which is the original one, what we do is that we use a fundamental waveform and other waveforms to represent it, which is what we're doing for the square waveform that we looked at earlier. So within from one cycle from here to here, you get to see that the green just move just half, what do you call it, just half one, right? So that's why it's called a fundamental. So it just has what's the name, one cycle like this, right? There's not a full cycle though, but it's just half cycle of it, right? So that's why I call it the fundamental. We just move half, right? The fundamental. The next one will be is that so you see, as you move on, so let's go back to this. This has a frequency of 2f, this is 6f, this is 10. So the frequencies increase, right? So this one right here has a particular frequency. So you just move within that the one cycle of the original waveform, it moves kind of like half, just like this, right? So when you go to the next one, which is the blue one, that's what we call the third harmonic, right? We just go over this very quick. It's not, but if it's something I don't need to, you can just skip it. And then here we have the fifth harmonic. Right? It's going to go over why they are called so, right? So within half cycle of the original, this one moves, the green one, which is said the fundamental, right, move just once, right? So let's see if within that particular time frame it moves just once, right? So kind of like one. When you go to the blue one, which is a third, it will move a multiple of the what do you call it, the fundamental one. So where's the blue? So it moves 1, 2, 3. So you see third harmonic, right? Yeah. So the yellow one, let's see how many times the yellow one will move within that same cycle or that same time period. So let's see. So that'll be 1, 2, 3, 4, 5, right? So that's the basic understanding for what I've been doing so far. So we'll explain why we skipped some numbers. So you'll be asking yourself why we don't see first harmonic or second harmonic or something, right? Or you don't see fourth harmonic or something. We'll explain that. Okay. So now we get the basic understanding that the main thing is that we have the the red waveform, this right here. This is just the understanding part. You can skip if you don't need this. This is the red one, the original one, right? But then in order to make it easy to represent, we break it down to the green, blue. Break it down to the green, blue, and yellow waveforms. So when you add these together, it gives you the original red waveform, right? And then we said that this fundamental, what do you call it, third harmonic and fifth harmonic. Okay, there's the reason to that. You see, for this particular waveform, when we started, we said the red waveform. We're still on the red waveform. It starts this way, right? Moves blah 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 and gets here. There's one cycle. The other cycle is just the same as the first cycle, but then flip the other way, right? So you see now instead of going down, now it goes up, right? And instead of going up this time, it goes down. It touches the what do you call it, the axis again, and then instead of going down, it goes up, right? So it's like flipped, right? So what this tells us is that this particular waveform is what is symmetrical, right? So you see we have this. When you flip it the other way and rotate it again, it's flipped the other way around. So we get to see that this particular waveform here is symmetrical. And then what happens is that when you have a symmetrical waveform and then you're trying to, what do you call it, a symmetrical harmonic, right, or non-sinusoidal waveform, and you're trying to use other waveforms to represent it, you end up using this what's the name, fundamental, and then the third and fifth. So you just be using odd, right? So let me write this out. So when you are representing a symmetrical waveform, you have to, we end up representing it using odd harmonics, right? Odd harmonics. And if you have an asymmetrical waveform, we represent it using even harmonics. Let me just go with this. So then if it happens that it's asymmetrical, represent it using what? Even harmonics. So that's how it goes. So that's the reason why for this particular one, we get to see that the original waveform, which is the red one, is what is symmetrical, right? And then the harmonics that we are using are actually odd ones, so they are odd multiples, right? So that's the main reason. So what we could see about this one that we represented here, this square harmonic that we wrote this square harmonic. So now let's clean this up and look at this. Okay. We said that this equation I've written right here. Let me clean this up. We've gone through this already. We said that this one that I've written right here is a square harmonic, right? And then when we looked at the frequencies, and we got to know that when we look at them very well, the frequencies of the ones that follow, right, are just even multiples of the original one, right? So when we look at this right here, we have the frequency, something like 2f. So we said for this particular one here, we end up getting the 2f, right? This one here is a 6f, and this one right here is a what? 10f, right? So you get to see that to move from here to here, multiply. The original thing is 2f, so let's see. So if you look at it very well, this is just 2f, so the 2 is out. So in actual sense, this one right here should be, take the 2 I get 3, right? If you take the 2 out, you get 5, right? So this is just to clarify something, because we said for AC quantities we have Vm sine and we have 2 pi f, right? So 2 pi f. So when we take this 2 out, take the pi out, and we take the t out, the only thing we left will be f for the first one. So for this one right here, the frequency is just f, right? This is 3f and this is what 5f. So multiples will be that here, you multiply this one by 3, the 3 multiplied this get a 6. When you multiply this one by 5, it gets 10. That's why it's that way. So looking at this square wave harmonic very well, you get to see that this is actually, what do you call it, an odd, we are using odd harmonics to represent the main function, right, or the main wave. So this will mean that the square wave form itself will be what? Asymmetrical. So that's all the meaning for this. But then we are going to look at one more thing. So now that we've gotten to write, understand the harmonics, and then why we write them those ways, we are just going to look at one more thing. The next thing we look at is that one value that's very important in applied electricity is the RMS value, right? And then for that, for any quantity that we have, we should be able to find out the equivalent amount. So we discussed this earlier, that if you have an average value, means that it's not that much accurate. But if you have the RMS value of an AC quantity, you should be able to know that, oh, if you apply that equivalent AC value through across a particular resistor for a particular time, right, you get the same amount of heat dissipated by the resistor if you have to apply the AC quantity, right? So that's why we are still interested in the RMS, or the effective value of AC quantities. So now we are looking at this. What it says is that we talked about RMS, right? And we said RMS. So we are finding the RMS of a quantity. You square the function, right? You find the area under the squared function. You find the mean and you find the root, right? The same thing for the harmonics. But what we do this time is that, you see, the harmonics we said is a sum of other functions, right? So if we are trying to find the RMS of a harmonic, what we do is that we take the peak values, right? A minute. We talked about RMS, but then we got to know that when it comes to sinusoidal functions, when we're trying to find the RMS of sinusoidal quantities, so let's say the RMS, whether currents of voltage, let's say RMS, whether current of voltage, let's use current this time. We're trying to find the RMS value for sinusoidal quantities, so for sinusoidal quantities, we just take the peak value, right? Oh, there's current, so let's use peak. What we do is that we just take the peak value or the maximum value and we divide by square root of 2, right? So that's what we said. And then we said for the harmonics, because it's a complex wave, we actually use other sine waves, right, to represent the whole thing, right? So what we are looking here is that even for this square sine wave that we're written here, we could clearly see that what we use, they're broken down, the inside ones are just sine waves, right? So if they are just sine waves and we want to find the RMS of the whole harmonic, that's what we do. It's just the same procedure, but this is a bit different. We end up taking the resultant RMS right? The resultant RMS of the individual sine function. So something like this. So let's see. There's a simple representation for it. The RMS squared. So there's one RMS. Then we have another RMS. Let's see. A2 squared. So that's how it's done. Right. So now we are going to do it for this particular example. So if you are trying to find the RMS here, what we do is that we look at the first one. So basically, this is the first one. This is the second part of the harmonic, right? And there's the third part of it. So looking at the first one, what was the peak value? The peak value is 1. So since it's just, if it's 1, so that will mean that we have 1. But then it's a sine function, so we have to take the whole thing. So that's 1 on root 2. That becomes RMS, right? And because you're doing resultant, we do the square. Go to the next one. Where's the second one? The second one is this. The peak value there is 1 on 3, right? So you're now getting 1 on 3, right? And then we put all these on root 2, and then we square it, right? Then go to the next one. Next one we have 1 on 5, so that will be 1 on 5, and put that on root 2, right? And then we square. So this is what will give us RMS value for that function, which is a square function, right? Square wave. So let's see what we get for this one. Okay. So most of the time it's very important that when you find a way to recognize a procedure that makes your work much more easier. So that's 1 on root 2, 1 on root 2, 2, and then we square this, right? Plus 1 on 3, 1 on 3, all on root 2, and then we square this. So now we have 1 on 5, all on root 2, and we square this as well. So this ends up giving us a 7. Let's see, 40, that's 0.7. That's 0.7587 since voltage volts, right? Look at the same example. Right, so looking at this one very well, let's look at it very well. What are the parts of the whole thing? We have this, we have this, and then we have this, right? So we could clearly see that for this particular one, let's start with this. The one here, the peak will be just 5, right? The peak will be this 5 here, and this one, the peak will be the 3 root 2. 3 root 2. What could you see about this one? You can clearly see that this one is just a number, right? So if it's just a number and there's no sign attached to it, or even if there was a sign and that's 10 to 1, now it's just a single number 2. So what we could say is that this value here, since it's not a sine wave, the full effective value, right, to be just the 2, right? So that's what happened through the process. So we're trying to find the IRMS, right? And we've identified the individual what do you call it, the peak values, right? So this one here is 2. This is the RMS for that particular one, so we just square it straightforward, right? For the one right here, the peak value is 5, so 5 on root 2. So this is the RMS for that particular portion. What do? We square it, right? Why? Because when we're trying to find the RMS of a harmonic, what we're doing is we're trying to find the effective RMS. What's the name? Resultant RMS. So that's why we do the square and then square it, right? So 1, 2. The next one will be that we have a 3 root 2. That's the peak value. What do? We do it on root 2, and then we square the whole thing. So The result is what will give us the RMS of the harmonic itself. Right, so we have 2 squared, then we have 5 on root 2, and we are squaring all, and we have 3. So let's do this first. 3 root 2 on root 2 basically cancels out, but let's put it, and then we square this side as well. Right. And now ends up giving us 51, root of 51 and 2. That's about 5 point something. Yeah, so that gives us 5.0496 right, and because it's current, RMS current amperes.